In this video, I will talk about our paper, Effective Evaluation Using Logged Bandit Feedback from Multiple Loggers. This work was done by Aman Agarwal, Soumya Basu, Tobias Schnabel, and Thorsten Joachims from Cornell University. Our work focuses on evaluating the performance of a user interactive system using historical log data from previous versions of the system. So let's first look at the general schema of such a system. The input is a context X, which describes the user and perhaps other parts of the environment, to which the system P0 responds with an action Y, drawn from some distribution conditioned on X. The user then interacts with Y in some way, implicitly generating a feedback delta XY. We would like to measure the performance or utility of system P0, which is the expected feedback delta XY over the space of context X and actions Y. As a quick example, consider a news website like the New York Times. Here, the context could be the reader visiting the page, the time of day, and other relevant information. The system would then take action by choosing which articles to display. The feedback is some relevant metric of goodness, such as time spent reading by the user. Now, A/B testing a new system can be risky, expensive, and time-consuming. So it's desirable to use the log data in an offline fashion. Crucially, this log data often comes from multiple policies, since systems are regularly modified and improved upon. We found that the standard technique of inverse propensity scoring to adjust for the mismatch between the logging policies and the target policy by bar can be highly suboptimal. In fact, as seen in this toy example, if the logging policies are sufficiently different, then dropping log data from some of the loggers can actually reduce the variance of the Naïve IPS estimator. The key insight is to reweight the samples based on how much their logging policy diverges from the target policy. Intuitively, the high variance samples are downweighted to preserve the signal from the low variance samples. This led us to formulate the Veighted IPS Estimator, which is guaranteed to have lower variance than the Naïve IPS Estimator, sometimes significantly so. Finally, we also formulated the Balanced IPS Estimator, which is inspired from the multiple importance sampling literature. This estimator also has provably lower variance than the Naïve IPS Estimator.